Okay, hello everyone, and thank you very much for watching this video, and thank you everyone for the good comments that I have received in the previous days. Thank you very much for your comments, suggestions. I would like to say thank you to all of you. That includes a few of my students and a lot of people around the world. Thank you for the support. And today the plan is to keep working on asymmetrical faults. Okay, probably you can see here this is the sample 3.2, and you are wondering, okay, but this class is related with asymmetrical faults, and the short circuit is a symmetrical fault. I mean, it's mainly three phases going together, bolted together, and that is creating the short circuit. And probably you are wondering why this gentleman is talking about three-phase short circuits. We are expecting that you are talking about line to ground or double line or a double line to ground. Well, my idea here is that a lot of people they don't realize that symmetrical components, this beautiful theory created by Charles Fortescue, this beautiful theory can be applied for the power system, even if the power system is working on symmetrical basis. Okay. Well, the job today is let's start with this power system, but I will be running three-phase short circuit calculations, but in this case, I will be using the theory of symmetrical components. That is what is new here in this example, okay? Well, let's start. Consider a simple power system. The single line diagram is showing here, showing below. I think you are familiar with this power system. It's the classical power system that we have been using for few classes. They are a generator, they are a motor, coupled to winding transformers, and a transmission line to 138 kV connecting both transformers. Okay. What is the job today? Well, the job today is quite beautiful because calculate the per unit subtransient fault currents at the phase A, B, and C if we are considering a three-phase to ground short circuit. Okay, three-phase to ground short circuit at bus bar number 2. Okay, okay. Let's start with the solution of this problem. And what you need to understand is that the first step for this kind of problems using symmetrical components is that we need to define, we need to calculate what are the terminal conditions, okay? The terminal conditions apply to the power system. And what I will do now is I will show you what I will do now is I will show you the terminal conditions, okay? Okay, I noticed something here, okay? Terminal conditions, we are talking about a three-phase, three lines to ground here, okay? Uh, in this case, what are the three terminal conditions? Okay, the three terminal conditions, you can see here, I have my generic power system at bus bar number 2. I will take phase A, B, and C connected together and then going to ground. That is the bolted three-phase ground short circuit, okay? Well, as you must remember, ground is the reference, voltage here is 0, and the terminal condition that we are imposing using this three-phase short circuit is that all the voltages must be equal to 0. Okay? Wow, this is quite interesting because if the three voltage A, B, and C they are 0, well, you must remember using symmetrical component if phase A, B, and C voltages at the fault point is 0, that means that the zero sequence, positive sequence, and negative sequence components of the voltage at the fault point are 0. And the next job for you is, okay, now we know the terminal conditions. We know the terminal conditions. And what we need to do is, okay, let's use the Thevenin models. We calculate the Thevenin models in the sample 3.1. And what I am doing now is, okay, terminal condition impose that the voltage in each sequence network must be zero. And what is the way that I can do that? Well, extremely simple, extremely simple. I will apply a short circuit. I will apply a short circuit at the uh, Thevenin for positive sequence, negative sequence, and zero sequence. What is the situation? Well, that the positive sequence is the only model that we have a voltage source, and that is the reason that that is creating the current moving here. Okay. On the other hand, in this case, they are not voltage source in negative sequence, and as consequence, this voltage is zero. And in zero sequence, they are not voltage sources. For that consequence, zero components, current components are zero. Okay. Well, the next step is extremely simple because we can calculate mm, from the positive sequence. We can obtain using basic circuit analysis here. The positive sequence currents will be the voltage, and that is the pre-fault voltage 1.05 per unit, divided by this Thevenin reactance, that is the positive sequence Thevenin reactance, and we obtain here the important positive sequence uh, positive sequence current. Okay. Next step. Okay, next step is quite interesting because we already know we have the value for the positive sequence. And from my previous conditions, terminal conditions, and then the network sequence network conditions, we know that they are not, there is not negative and zero sequence. And the next step is, okay, I know the symmetrical components because I already calculated, and I need to know what are the asymmetrical components. That means A, B, and C. Okay? Well, it's quite interesting. What we need to do is something very simple. We use the theory coming from Fortescue. We use symmetrical components. We use the matrix A. And in this side of this equation, you will find the symmetrical components, but in this case, the zero component is zero, and the negative component is zero because they are only positive sequence when we are using a short circuit, a three-phase short circuit, okay? Then we put the number together and voila. Now we obtain here the current that is moving on phase A, phase B, and phase C. And I think all my students, they will realize that we have over there the currents that they are moving on line A, B, and C. Okay. Um, you can see that the procedure was extremely simple because you are using symmetrical components, and symmetrical components make your life easy in terms of the calculation of those currents on A, B, and C. Okay. Okay. Something that I want my students to understand is those currents, those phasors, they represent a three-phase system, but in this case, this is a mm, balanced three-phase system, okay? And also, they preserve this beautiful property coming from the three-phase systems where we have 120 degree apart between the between the phasors, okay? If you allow me to use my ugly handwriting, okay, um, we can say that the reference is here. Let's say this is 0 degree. And if we are creating the phasor diagram, you will realize that the current for phase A will be here, and we will say this is A, okay? And then we have the current C here, that is plus 30. This is minus 90 degree, and this is the current C. And then we have here 180. You must remember this is 180 degree. And here we have the other phasor, and in this case that is IB. Okay. With this ugly handwriting, what I'm trying to show you is that in this case we are having the beautiful oh Jesus, yes, it was the mistake. It's 150, positive 150 degree here. Okay, now it's clear. Now it's clear. That is the good news of plotting the phasor diagram, that you can identify if there is any numerical mistake here. Okay, but what I want that you can see is, in this case, this is a ABC sequence. We have here the current A, B, and then C. And as you can see, using the symmetrical components, you can get the beautiful three-phase representation, and it's useful for you to identify any possible mistake. Okay. Let me keep going with my explanation. The next step is extremely important. The next step is for short circuit analysis, okay, per unit currents. They are interesting, they are important, but when we are working with real physical components, the current in amps, it's the important indicator, okay, because it will be defining many properties. For instance, the capacity, the short circuit capacity of bus bars, but also breakers and many other components. Okay, what I will do now is the three currents, they have the same magnitude, okay, and multiplying the per unit value using the proper base. In this case, we are using 13.8 kilovolts. We obtain here that the final short circuit current is around 31 kiloamps, okay? Okay, well, thank you very much to all of you for watching this video, and thank you very much for taking this class. I hope you enjoyed that. Using symmetrical components, we will be able to calculate three-phase short circuits. Thank you very much for your attention. Thanks.